In this video, I first look at the sideband noise of this oscillator. The reason is I want to improve my test system. Try to get lower noise of the reference oscillators, because that will make the time shorter when I use them for optimizing my much better oscillator with many crystals in it. Here is the phase noise as seen in Linrad. The amplitude and phase modulation is extracted with a coherent detector. In the baseband here there is a narrow filter. It is 0.05 Hz wide approximately, 0.1 Hz per division up here. The carrier that comes out through this narrow filter is multiplied with the entire bandwidth, and that creates an I and a Q signal, and if the phase is not shifted by the filter, the amplitude modulation comes in phase and the phase modulation comes 90 degrees. So what I do is I take that complex function and do the Fourier transform, remove the DC component by shifting the phase accordingly, and then I have AM and FM modulation on the signal. The Fourier transform looks like this. Green is channel 1, magenta is channel 2. The yellow trace is the correlated spectrum between those two. And it has a straight line like this, but at about here, that's 0.3 Hz, it bends upwards. Now, for this procedure to work, as I written the code, I have the same filter for both channels, so the signal must be very close to each other, nearly the same frequency. To achieve that, they are phase-locked to a reference, a frequency-shifted rubidium source. And that phase locking could introduce noise from the rubidium source that would be correlated in the two channels. And that could have something to do with this, which I will check later. There is, of course, amplitude noise, but it is very much lower. At 1 Hz offset, here, the Wenzel oscillator is at -120 dBc per Hertz. My test oscillators, the uncorrelated signal, is about 2 decibels higher here, but it contains the noise of my reference oscillators as well as the noise of the Wenzel oscillator. And since it is not as much as 3 dB above, it means that these oscillators are better than the Wenzel oscillator. Not much, but a little bit. Here is the Allan variation, recorded during the same 13 hours. The yellow trace is what Linrad believes is the Allan deviation of the Wenzel oscillator. And it's interesting to see that in the region from about 5 seconds to about 50 seconds, the two series of measurements with the two different oscillators give exactly the same result. And the yellow trace is the correlation between those measurements, and it's the same as the measurements. At shorter times, closer to the carrier, the green channel, channel 1, is a little bit more noisy than channel 2, and the correlation is not so strong. It means the yellow curve is below those two. And here above 100 seconds, I don't know if really one can trust the statistics. I had expected at some point up here the noise would be dominated by the noise of the rubidium source. But, well, this is how it looks. The frequency versus time is fairly flat. It doesn't slope much. The slope we can see should be the frequency drift of the Wenzel oscillator. And then, here, I entered the room and made some things. I think the Wenzel oscillator was affected, but I'm not sure. Some instability with something. Anyway, if I click on this box, I get two traces. The yellow is the frequency difference between the two channels. So that's the noise, some noise of my reference oscillators. The blue trace is the phase shift between the two channels. And it shows that the phase locking has been very successful. The phase has been drifting slowly, which is a bit odd, because that's a slow component of the frequency drift. Could be something with the temperature changing slowly. This is after all a couple of hours. This is how the loop filter for the phase locking is arranged. A resistor, lowest value 1 kilo ohm, that's what I have been using now, gives the shortest time constant. The very big capacitor and the 10 kilo ohm resistor is to avoid oscillations in the PLL loop. I will now change from 1 kilo ohm to 100 kilo ohms. That's a factor of 100 on the time constant, to see whether there will be a difference. That will be 6 steps here for the two channels. Well, that was too much to take at one step, so I go back 2 steps here. The main resistance is 44 kilo ohms now, and it's clear that the signals are far less noisy in frequency. I will go up to the 100 kilo ohms and wait for locking. Maybe I have to do it in 2 steps. It is very different now. Here, fairly small frequency deviations, but a lot of high-frequency noise. Here you can see the difference between my two oscillators. The channel 2 one is much better than the one in channel 1. The frequency differs by 0.5 millihertz, roughly. If I look at the phase, you can see that the phase is drifting downwards, slowly, turn after turn. So when I wait long enough, the frequency will be on the average the same. I reset here to start a new measurement of Allan deviation. And also restart here to get a new set of phase noise. And we can see here that the phase noise is smaller. Here it is, well, it is different. This has been running for 4.5 hours now, and I see a clear difference. You can see here the phase noise of the Wenzel oscillator looks perfectly like a straight line now. The bending that started here somewhere has disappeared. It was caused by correlated noise on the two reference oscillators. Now with the 100 times larger time constant, the place where this happens is moved down to very close to the carrier and not important anymore. And we can see here that the two reference oscillators are significantly worse than the Wenzel oscillator when it comes to noise at 0.1 Hertz offset. It's a difference of 7 decibels or so. At 1 Hertz, on the other hand, they are very good. The Allan deviation is quite different now. At 10 Hertz offset, my oscillators are no good, so I see the correlation between them is very weak because they suffer from their own noise. And here you can see frequency versus time. And I can click here, and the blue trace shows that the phase rotates a couple of turns. So they are really uncorrelated, these signals, in the time scale of 500 seconds or so. I'm satisfied to find that the 100 kilo ohm resistor is big enough to eliminate the problems of correlation between the two oscillators. And one more thing, I think there was noise from the pace lock itself that contributed to the high noise level at 10 seconds, or even below. I don't remember exactly, but there was some noise in this region that is now not present anymore. And noise from the PLL circuit, it's on CMOS thing, may have reached the oscillators, but now with that big resistor, frequency components at 0.1 Hertz can no longer come through. Now I plug in the soldering iron here. That has an immediate effect on the frequency, which drops about 1 millihertz. The soldering iron is only 60 watts, so something is changing when the 220 volt supply is changing. I changed this power supply one step, 1 millivolt. This gives a similar response, although much smaller, and this indicates that the soldering iron caused a drop of about 10 millivolts by eye measure. And change the voltage scale to see better, 0.05. Now I can see 1 millihertz clearly. And then I see the 10 millivolt step was worse than connecting 60 watts to the same 220 volt supply. Line regulation is not very good for this power supply. But it's clear that the power company that delivers the 220 volts to me is doing a very good job in holding the voltage constant for me. And note that these two fairly strong excursions, about 4 millihertz in the worst case, has changed the Allan deviation completely. I have replaced the Wenzel oscillator by this rubidium source, LPRO 101. While searching for the resonance, it sweeps a fairly wide range, as you can see here. Plus minus something like 100 hertz or so. It was more than that, down to 200 hertz below 10 megahertz. and 100 Hz above. There is a significant frequency drift just after it started. Here I was running the scale much faster, but here you can see the exponential going towards something up here. And I will wait for a while. Now it seems to have stabilized. I changed the scale to see what happened. And you see it has been about 500 seconds before I reach this fairly stable. I clear the screen and restart. It takes a long time for the rubidium source to become stable. This is 1.5 hours and the frequency drift is 2 millihertz. And that affects, of course, the Allen deviation graph. I don't know how long time this normally would take, but the stability of the Wenzel source is much better. And it is when compared to another rubidium source, which has been running for weeks. And the phase noise looks horrible in the close range. 0.1 Hertz, minus 50 decibels, and 1 Hertz, minus 65. Here is 4 hours with the rubidium source. It is stable now, and the Allen deviation looks reasonable. I think that above 300 seconds or so in this region, the statistics is not at all good enough. The noise of the oscillators probably goes up like that and not down like that. It's just a statistical phenomenon. And the correlation between them probably would continue this straight line a little bit more, I don't know how long, and then it would turn up, reflecting the instability of the rubidium oscillators in longer time scales. I switch to the Hadamard deviation, and it looks more reasonable out here. Maybe this is real, that the noise is increasing from something like 300 seconds. I will leave this for some more time. This is 9 hours and 10 minutes, and what I see beyond 200 seconds or so is obviously unreliable. My oscillators are not good enough for that. One interesting thing is you can see here at the end of the time of the frequency versus time. When I enter the room, I stir up the air and the temperature changes on the oscillators and they drift apart now by about 1 millihertz. When I look at the phase, the blue trace is the phase difference between the channels, and you can see how it becomes much steeper here. And the yellow is the frequency difference between the two channels, which should stay at a constant value, but it has dropped here. But that is okay because I'm looking for the correlated modulation between the channels, and as long as the signal stays well within the passband, it doesn't matter if it changes frequency a little. An interesting thing is the noise floor up here, containing noise birds coming and going, and the noise floor is very high. I made a mistake. I was feeding this LPRO 101 with 15 volts, not 24 as I should have done. Now, when feeding it with 24 volts, performance is much better. And I can see now the channel 1 oscillator is much better than channel 2. The difference is that channel 1 is stuffed with cotton to reduce air circulation inside. I will do the same with the channel 2 oscillator to see if that makes a difference. Here is the phase noise. Now I think it's the true phase noise of the rubidium source. It is about 62 decibels at 0.1 hertz. And here 75 at 1 hertz offset. And it all looks okay. And the noise floor looks nice and doesn't have these instabilities I had before. I have increased the resistor in the loop filter to 220 kilo ohms. So the time constant is very long now. This is what the channel 2 oscillator looks like inside. I have filled it with cotton like this. The frequency has changed by 220 millihertz. So I will tune a little bit. Now it has been very nice for a while here, and then suddenly something happens. I don't know what that might be. The frequency of this could be associated with the time constant of the PLL loop. The temperature changed and affected the oscillator, and then it makes some oscillations. But that's it doesn't look really like that. I don't know what might have happened. I do know that at this point in time I entered the room here, and this looks like the steepest change. Well, this is clearly a more dramatic change than what I had here, because I stepped inside here. It seems that the temperature coefficient is in opposite directions for the two oscillators I have. Well, this doesn't really matter. This is noise very close to the carrier, and I'm mainly interested in the phase noise and amplitude noise down to about 0.1 hertz, and then this is perfectly okay. I placed this handkerchief on top of the oscillators to change air circulation around the oscillators. And here is the result. I had to change the scale by a factor of 10, and as you can see, channel 2 moved about 50 millihertz, while channel 1 moved about 20. So the problems I see is temperature variations. It has taken about 2000 seconds for this event with the handkerchief to recover. This will be fine. The frequency is kept within at least plus minus 1 millihertz. Often much better than that. So the evaluation of modulation as done by Lienrad will be okay. And there is no correlation in the noise from the two oscillators at frequencies above something like 0.01 hertz from the carrier. There has been an event here that is correlated. It could be temperature, and I cannot say for sure the frequency content of it, but I don't think I will have any problem with correlation between the local oscillators when measuring down to 0.1 hertz from the carrier, at least. I have changed the loop filter like this. Smaller resistor and smaller here as well. This seems to make the oscillatory behavior a little less pronounced, and of course the bandwidth is larger now, so but 0.1 Hertz is certainly okay still. The phase noise has gradually become bad. You can see how this was narrow and how it has widened. And also, of course, in the analysis here of the sideband noise. And when I came here, the width of the channel 2 was acceptable, but it has been very high during the total 9 hours that have elapsed. I think this may be caused by a too low voltage on the frequency controlling capacitor diodes. It had dropped below 1 volt. So I have increased the fixed capacitance. There is a little screw for that. And now you can see how the frequency has changed and it's approaching the correct frequency. Now I have almost 2 volts on the capacitor diode. I will wait for a while to see what happens here after my change. And also maybe increase further. It's very slow, these processes, because of the long time constants. Now I have 1.2 volts on the capacitance diodes. And I can see a clear difference here. It becomes more visible when I look at the frequency difference between the two channels. It's the yellow trace, and you can see it is very different. But the higher frequency noise that I can see here is clearly weaker. And one can see here, it is a little bit narrower, but it's not at all as good as it was when I started this measurement. So I will increase the capacitance. I now have 2.5 volts on the capacitance diodes, and still the noise is high, as you can see here. Maybe it was a bad idea to reduce that resistor from 10 kilo ohms. I will put it back. I have restored the original components, but still the channel 1 oscillator is significantly more noisy than channel 2. It's clearly seen here, and of course here much better. But at 0.1 Hertz, the difference is maybe 4 decibels. It means that the level of sideband noise is much higher in channel 1 than in channel 2. Because the correlation spectrum, the noise of the Wenzel is down here, and then it is perhaps 2 decibels to the magenta trace, and another 3 decibels up to the green trace. But I don't know what to do about it. The reason could be bad polystyrene capacitors. It's a known problem. I have ordered better ones, hard to get, and I will wait until I read them and see if that helps maybe. I have swapped the loop filters between the channels, these components, but the result is not what I expected. I had thought maybe there was a noisy capacitor, but no, there is something else. There seems to be a noisy thermoelectric voltage somewhere in the connectors. This is the arrangement, BNC connectors. So I will clean them carefully and check that they have gold contacts, all of them, and the same for both oscillators. I got a lot of black dirt on the cotton pins while cleaning these connectors. One of them had a silver center pin, the one on the cable. I have replaced that with one that is gold plated. So the center conductor is gold against gold all the way. Here is the original frequency versus time. You see how the noise looks. This is where I swapped the filters. And here I have cleaned the filters. not really waited long enough, but it looks even better than here. So to me this is a new phenomenon. I would call it thermoelectric noise in dirty connectors. And the phase noise graph starts to look interesting. I don't think I made a reset early enough, so I will reset it. But it's clear, looking here, this is even narrower than what I had here. Things look much better now. This is only 1.5 hours, but you can see the frequency versus time. This is the same scale as before, and it looks not as noisy. And here it looks quite narrow. Up here I can change the color scale by 5 decibels, from 50 to 45. And then it takes some time before it refreshes up here. I can look here and compare with this. And it seems I have restored the performance I had at the start here. And I don't know what is the cause for oscillator in channel 1 to be about 5 decibels more noisy than channel 2 at 0.1 Hertz. Could be polystyrene capacitors, could be something else. Anyway, this is what I have arrived at, and I will let it be like this, because now I have a new project looking at polystyrene capacitors. I received a parcel today with ones that are welded rather than just squeezed aluminium mot tinned copper wire. I have set somewhat less demanding parameters. It starts now at 0.1 Hertz, and this has been running for 2 hours and 12 minutes. The noise floor, as indicated by the imaginary part at 1 Hertz offset, is at about minus 128 dBc per Hertz. And it's more difficult to see where it is at 0.1 Hertz, but it's well below the level of the Wenzel oscillator, which is minus 93. So this looks more reasonable than before, but not much. The result at 0.1 Hertz is the big improvement. Here is what I would call my standard parameters for evaluation of oscillators. I'm using linear frequency scale and computing the average level in decibels from 0.7 Hertz up to 2.5 Hertz. The result comes here, and you can see the first time it's minus 129. Then there were several blue points which were ignored because then correlation was negative. And then it slowly converges. And after 8 transforms, it's 125. But I have to wait for a while to make sure that the yellow trace is well above the red dots, which is the imaginary part that indicates the noise floor of each measurement. After 5 minutes I have 34 averages, and the value is minus 124.08. 15 minutes, 126 averages. The average is minus 123.65. After 25 minutes, 218 averages. The average is minus 123.79. The noise contained within the yellow trace is at the level of the imaginary part. It's a little bit more than 10 decibels below. So 10% of the power seen here is noise. And if I wait long enough, it will be 0, and that will not change the average value by more than a couple of tenths of a dB. So to get an accurate result within a quarter of a dB, I need to run this for something like 15 minutes. When the level is at minus 119 dBc per Hertz at 1 Hertz offset. Now I want to measure something like minus 132 dBc per Hertz for my best oscillator. That is 13 decibels better than what I have here, means 20 times lower, means 400 times lower measurement time. That's a long time. So I cannot hope for as accurate measurements, which makes optimization a little bit harder.